So, good evening, everybody. My name is Mr. Smith. Thank you for coming to this webinar on proton NMR for AQA A Level Chemistry. This is what we're going to have a look at today. We're going to look at how we use proton NMR to determine the structure of molecules. A vital facet of that is being able to identify equivalent protons. We'll look at the relative intensities, the importance of the solvent and use of TMS, how chemical shift is used to help identify proton environments, and the splitting patterns as well. So here we go. Okay, so a little bit of background into the idea behind NMR. This is probably going quite a bit beyond what you need for A-level chemistry. If you're an A-level physicist, you probably know a little bit more about this, and this is very much a simplified description of what's going on. All nucleons, protons and neutrons, have this quantum property called spin. It's kind of a complicated thing related to angular momentum, but the simplified form, as far as we're concerned, is that protons and neutrons can have a spin of +1/2 or -1/2. And it's not like all protons are +1/2 and all neutrons -1/2. It can be either or. The important thing to be aware of is that if you have a nucleus with an even number of protons and neutrons, the spin numbers cancel out and there's no overall spin for the nucleus. So something like carbon-12 has no overall spin. But if you have an odd number of protons and even number of neutrons, they don't all cancel out and you have an overall spin. So our protons have an overall spin. You could have an even number of protons and odd number of neutrons. They also have an overall spin, which is why carbon-13 also exhibits NMR spectra that we can interpret. Now, the reason we can make use of this property of nuclei is that a nucleus with an overall spin generates its own magnetic field, and that magnetic field of the nucleus with spin will interact with an external magnetic field. If the external magnetic field is sufficiently large, what happens is that the nuclei with spin will align with that field, much like putting a bar magnet or a piece of metal or something into a magnetic field. It may spin to align with the field. It's a similar kind of principle behind this. So a little bit more information. The way that nuclear magnetic resonance works is that your nuclei will line up with your applied magnetic field, but if you can apply the correct frequency of energy to those nuclei, they can align themselves in the opposite direction against the field rather than with the field. And that is a higher energy state, and this process is known as resonance. That's where the resonance in nuclear magnetic resonance NMR comes from. So you can think of it like this. This is these two bars here represent the low energy and high energy possible orientations of the nuclei. The gap between the two corresponds to a particular frequency of radio waves. So if you apply your nucleus with a sufficiently large magnetic field, you then hit it with radio waves and they will align against. And the intensity of the radio waves and the intensity of the magnetic field tell us something about those protons. It tells us about what we call the environment of the proton. Typically, that's anything that is linked to the proton within 3 bonds. So the energy required, the energy gap, the intensity of the magnetic field depends upon the environment of the proton, and that gives us information on the structure of the molecule. Okay, so on to the next slide. So you need to be able to identify what we call proton environments, and particularly equivalent proton environments. Those are the ones that are said to be in identical environments when you consider all the other atoms up to 3 bonds away. And an equivalent set of protons produces one specific signal in NMR spectroscopy for protons. And the intensity of the signal is proportional to the number of protons within that particular environment. So it gives us some information on the nature of the molecule itself. So a couple of examples then, 4 examples in total. And I'd like you to work through this as I do this. We're going to identify how many different proton environments we have for these 4 molecules, starting with the one at the top. So this is 2-bromopropane. And if you have a look at it, you can see that you've got protons on carbon 1 and protons on carbon 3. They're considered equivalent because they're bonded to a carbon, and that carbon is bonded to a CH-Br group. That applies to both sets of protons. That makes them equivalent to each other, which means they'll appear as one signal. The proton in the middle, on the carbon number 2, with the purple circle around it, that's a proton on a carbon, which is attached to Br and attached to 2 methyl groups. So that represents a second environment. So we have 2 sets of equivalent protons here, and the ratio of the intensity for each environment will be 6:1. The red protons being 6 and the purple one obviously being 1. Second example, 3-bromopentane. We have our environments for our methyl groups at the end. There are 3 equivalent protons bonded to carbon, which is bonded to CH2, and that applies to both. That makes them equivalent. Then our CH2 groups in the middle. They're each bonded to a methyl group and a CH-Br, that makes them equivalent. And our CH in the middle, our H bond to carbon, which is bonded to Br and 2 CH2 groups, that's a third unique environment. So this time we have 3 sets of equivalent protons that will produce 3 signals in an NMR. And this time the ratio of intensity will be 6:4:1. Okay, looking at the third example, 2-bromopentane. This one is slightly different. Moving the bromine atom along the position isomer means that it will produce a different NMR signal. This is where proton NMR is very powerful, because unless you use the fingerprint region, you can't tell between these molecules using infrared. NMR will do it though, and will do it really well. So let's go through. This time, if we look at the red and the yellow methyl groups, they're not equivalent because one of them is bonded to the green CH2 group and the other is bonded to the purple CH, the hydrogen bonded to carbon, which is bonded to bromine. And we have another CH2 group in the middle in blue, which is different to the green one. The green one, 2 protons bonded to carbon, which is bonded to CH3 and CH2. The blue one in the middle, 2 protons bonded to carbon, so far so good. But this time we're bonded to CH2 and CH-Br, that makes it different. So we have 5 unique environments, 5 sets of equivalent protons, and they will appear in the ratio 3:1 to 2:3. Okay, last example. We have 2-bromo-2-methyl-pentane. Going from left to right, we have our CH3, CH2, CH2. Our CH3 is different to our CH3s at the end, and our 2 CH2s are not equivalent to each other. One is bonded to CH3 and CH2, that would be the blue one. The green one is bonded to a blue CH2, and the carbon atom to the right, which is bonded to 2 methyls and bromine. The 2 methyl groups at the end, they are equivalent to each other. You've got 3 protons bonded to carbon, which is bonded to CBr. So that makes those equivalent to each other. So in this case, and I've just overshot it slightly, so I'll just go back a second. 4 sets of equivalent protons in the ratio 3:2 to 2:6. So that's how you identify your equivalent protons and their relative intensities. I think a question's just come in. I'm just going to check that. To what extent does a bromine affect the protons in the structure? Say if there were another CH2 in the chain, would there be another different region? Okay, well, it would depend upon where the CH2 is. So just to make sure I understand the question. The bromine affects the protons in a couple of ways. It affects it in terms of its chemical shift, and we'll look at that a little bit later. Essentially, you are looking in the middle of the 2 CH2 currently there. Are we looking at molecule 2 or molecule 3? Just answer that question for me so I'm really clear, I can see your question properly. Molecule 4 as if it was extending a chain. Oh, okay. Well, if you put a CH2 group in between these two here, for example, it wouldn't be a symmetrical molecule. So you would have, let's see, you would have the unique environment there. The two CH2 groups either side would not be equivalent to each other because the one that we're imagining between yellow and purple will be bonded to CHBr and CH3, whereas this one will be bonded to CHBr and CH2. That would make it a unique environment. Now, if the CH2 group was between purple and blue, then we would have our unique environment for CH3 at the end, our unique environment here. We would have a CH2 bonded to CHBr and CH2. That would also be unique. We would have CH2 bonded to CH2 and CH2. That would be unique. And then we would have our green CH2 bonded to CH2, CH3. That would be unique. And then we'd have our CH3 at the end, which would also be unique. As a general rule, you look up to 3 bonds away from the proton and you look at everything that's 3 bonds away. And if you can describe 2 groups in identical ways, looking up to 3 bonds away, then they will be considered equivalent. But if there's a slightest discrepancy going up to 3 bonds away, that makes them non-equivalent. And that slight discrepancy does include having 2 protons rather than 3 or 1 proton rather than 2 in the environment. That makes it different. Okay, so we'll move on to the next one now. So the relative intensity of the different signals that appear. So we can get quite a wide variety of signal types in proton NMR, and we'll look at them in a little bit more detail later. The area under the signal indicates the relative intensity, which gives you an indication of the number of protons in that environment. But the problem is they're usually quite difficult to determine because of the nature of the signal that's produced. It would take too long and it wouldn't really be worth your time to actually go to the trouble of working out the area under the signal, so we simply don't do it. What you will get is information in the exam. Information sometimes appears next to the signal in the form of an integration curve with a numerical value next to the integration curve, which indicates, relatively speaking, how many protons are in that environment compared to others. Or you might get the information in a separate table. So for example, here's an example of the NMR of ethanol. And as you can see, very hard to see how much area there is under the curve. So they've given us these integration peaks or integration curves, and the number next to them indicates the relative number of protons in each signal. Now, as it happens on this example, the whole numbers, they're often not whole numbers. You might see something like 0.6, 1.2, and 1.8. So you'd have to divide them all by the smallest number to get a whole number ratio, or something that can be easily converted to a whole number ratio. They're usually reasonably sensible, so you shouldn't cause you too many problems. Okay, so that's relative intensity. Now, the solvents and the use of TMS, we'll talk a little bit about this because this is important. The samples need to be dissolved in some kind of a solvent before we can analyze them in the NMR machine. Now, it stands to reason that if your solvent contains protons, it's going to show up, and that's obviously not going to be any good, so we can't have that. So you need a solvent that simply doesn't contain protons. Tetrachloromethane is a commonly used solvent. It's a very good non-polar solvent. 2 disadvantages: it is non-polar, so if you've got a polar sample, it may not dissolve it very well. And it's also highly toxic, so I don't really care, it's fine, of course, but it's not the only solvent we have available to us. Deuterated solvents are very popular. What I mean by deuterated solvent is essentially D is used as an indicator that we have hydrogen, but in the form deuterium, hydrogen 2. Because hydrogen 2 has one proton and one neutron, it won't show up. It has no overall spin. So it won't show up on NMR. Deuterated water, D2O, or heavy water is sometimes used if you need a good polar solvent. So it's something, you're using something that will dissolve very well in water. As long as it doesn't contain hydrogen H1, then and it's a good solvent and it will dissolve your sample, then it should work. Of course, you want to be sure it won't actually react with your sample as well. Now, TMS, tetramethylsilane, this is used as a reference to measure something called chemical shift, which I'll talk about a little bit more very soon. Essentially allows you to compare one proton environment with another. That is tetramethylsilane. Excuse me. That's tetramethylsilane. It is an analog of dimethylpropane, where the central carbon atom has been replaced by silicon. So why do we use tetramethylsilane for our reference signal? Well, the protons in TMS, they're more shielded than in almost all other compounds. What I mean by shielding? Well, the electrons that are in the hydrogen's covalent bond can have the effect of shielding the hydrogen nucleus from the magnetic field. So if hydrogen is, say, for example, bonded to a highly electronegative element like oxygen, we say that the proton is de-shielded, and that means that a less intense magnetic field is required to cause the hydrogen nucleus to align. But in TMS, like the shared pair of electrons is closer to hydrogen than in most other compounds that we might carry out an analysis on, which means that it is at an extreme, what you might call sort of an extreme side in chemical shift, which we'll look at in a minute. It will make more sense when we get there. So it's a good point, a good starting point as a reference for protons and all of their environments. In TMS, all of the protons are equivalent, so you only have the one signal. It is non-toxic and it is chemically inert, so it's not going to react with the sample and change it into something else. And it's quite volatile, so you can remove it from your sample afterwards should you need to quite easily. That's the reason why we use TMS as our reference. Okay, so now straight on to chemical shift then, so I can give you a little bit more information on this. I've referred to it already. Okay, chemical shift is a scale, and it compares the intensity of the magnetic field required and the radio waves required to produce resonance. And it compares it with TMS and with the protons in the sample. It compares the two. It's, this is going beyond really what you need. It's a measure in parts per million in terms of the magnetic field required. Okay, question coming through. Why is TMS needed? Can you do NMR spectroscopy without it? You can, but chemical shift gives you important information on the proton environment, and without TMS, you have nothing to compare with. By comparing the position with TMS, you can determine information on the proton environment, and we'll look at some examples of that in a moment. Essentially, because the protons are very shielded in TMS, you need a more intense magnetic field to produce resonance. All other protons require a less strong magnetic field. They're measured in parts per million. You don't need to know all of the details behind that, and I don't really want to get into it too much. You're not expected to be able to do TMS calculations for chemical shift. If, for example, if a nucleus has or a proton has a chemical shift of 5, that means that you require a magnetic field 5 millionths less to produce resonance with TMS. So it's a comparison, but like I say, for A-level chemistry, you're not required to be able to make those sorts of comparisons in detail. You just need to be able to identify the chemical shift of different protons. Question coming through, are there any viable alternatives to TMS? Yes, I'm sure there are plenty. We're going to have a look at a spectra later on that I've borrowed, and I think they used a different reference there because it doesn't appear in the same position. There are other things that you can use. It probably depends upon what you're analysing. Okay, now this is a terminology that you may come across. Protons with higher chemical shift, they're said to be downfield. When you look at an NMR spectra, chemical shift 0 is on the right-hand side and it moves to the left. So anything to the right we say is upfield, anything to the left we say is downfield. So anything that's downfield, anything further to the left, they represent de-shielded protons. So those are protons that are much closer to highly electronegative, it should say electronegative, that's a typing error, it's come up there, sorry about that. Electronegative atoms, that's an autocorrect issue in there, which pull the electron density away from the protons, and that reduces the strength of the magnetic field required to get it to resonate. Okay, so let's have a look at a couple of examples for chemical shift, and what I'm going to do now, hopefully you'll be able to see this. I'm just going to bring up the, it should be appearing on your screen. This is the NMR chemical shift data. That should be on the latest AQA data sheet. You'll get this in your exam. So what you need to be able to do is to compare the proton environment as per the chemical shift data and compare it correctly with the protons in your molecules. So let's go through one by one. So if we look at these protons here on the left-hand side, 3 protons connected to carbon, which is connected to CH2. If you have a look to the right-hand side, we have a CH3 group connected to R. R in this case can be CH2, that's absolutely fine. So these protons, there are 3 equivalent protons, they're next to a CH2, which we'll class as an R group, so they'll have a chemical shift somewhere between 0.7 to 1.2. If we look at the second one along, this time we have a CH2 group, which is attached to a carbon on the left, which could be an R group, and a carbon on the right, which could also be an R group. So that will correspond to a chemical shift of 1.2 to 1.4, 2 equivalent protons next to R2. Look at the third one. Again, we have CH2, which is next to a CH2. Now, this time it's next to a C carbon atom, which is attached to Br and CH3. Is the bromine going to have any effect? Well, technically speaking, we probably would expect it to have a little bit of an effect because it's within 3 chemical bonds. But as far as AQA are concerned, chlorine and bromine only have a significant effect. They only appear on the table when you have protons that are attached to carbon and a halogen attached to the same atom. So the halogen is not attached to the same atom as the same carbon atom as these hydrogen atoms here, which means we can take this carbon atom here as another R group. So we would expect these protons to have a chemical shift of 1.2 to 1.4. In reality, I'd expect them to be a little bit higher, but as far as AQA are concerned, they're not asking you to go into that level of detail. Then we have 2 equivalent methyl groups over here. They're all equivalent and they are next to an R group. It's this one here again, CH3 connected to R, 0.7 to 1.2. So they would appear as a single signal with relative intensity 6, somewhere in the range 0.7 to 1.2. So that's the information that you can get from chemical shift. You can get their relative positions on the spectrum. We'll have a look at an example in a moment. Okay, so what if we look at a different molecule? This time we have 3-bromopentane. Our hydrogen atoms, part of our methyl groups at the end, they are equivalent. They are on a carbon atom which is next to an R group. So it's this 0.7 to 1.2 again. So yeah, 0.7 to 1.2. And the 2 in the positions 2 and 4, they are equivalent to each other. They are joined to R2. Remember, it doesn't matter that the carbon atom next door is joined to bromine. as far as you're concerned, you can treat this carbon atom here as an R group. The two R groups do not have to be identical to each other. It's just as long as they don't have some of the other kind of functionality that we would look at further down here. As long as that doesn't apply, then we treat them as R groups. So they'd be 1.2 to 1.4. And then our proton on carbon atom number 3, well, we have a bromine atom here. So that would apply here. I know it says H2. It doesn't actually matter whether there is more than one proton or 2 protons in that environment. It will be classed as a 3.1 to 4.2. It's a proton on the same carbon atom as bromine. So that will be 3.1 to 4.2. Okay, let's have a look at an ester this time. Question coming through. What if the parts per million on the graph is at a number that counts for 2 different proton environments? Ah, yes, of course. I see what you're saying. Some of them do overlap, and yes, it is a pain, to be honest with you. What should happen as far as the exam is concerned is that the splitting pattern, which we're going to come on to next, will allow you to determine which one is which. So for example, we will look at this later, but these 2 first groups here, the proton on an alcohol functional group and the protons of a methyl group, they could have very similar chemical shifts, but this proton on the alcohol will always appear as what we call a singlet, where these may not be a singlet. And what should happen in the exam is that you should be given enough information to be able to determine them apart. So these wouldn't be a singlet, there'd be a different type of signal, which we're moving on to soon. So that, so you'll be able to get around that. Question, yeah, enough comment coming through. So you'd need to use several pieces of data to correctly identify the correct functional group. That's it exactly. One of the example questions that we'll look at a bit later uses infrared and proton NMR to try and identify the molecule. So you will always be given enough information to piece it all together. The skill is being able to interpret everything that's in that information, but they're not going to try and trip you up. They're not going to put you in a position where 2 proton signals actually you wouldn't be able to distinguish. They're not going to put you in that position. They'll always give you enough information to be able to piece it all together. Okay, so let's have a look at the ester then. So we have our protons at the end of the molecule, part of the methyl group. And yeah, sure enough, again, they are attached to a CH2. The CH2 is classed as an R, so they'll be in the range 0.7 to 1.2. Look at the ones next door though. So these are protons attached to carbon, which has got a CH3 one side, so that'd be classed as an R group, but the other side, we have our carbonyl group. So if we have a look through, we have a proton there attached to carbon, attached to carbonyl. Is there anything else that appears to match? That is the only one. So that would have a chemical shift of 2.1 to 2.6. So this could be, in this case, it's an ester. It could be the carboxylate part of a carboxylic acid, or it could be an aldehyde, or it could be a ketone. The point is the protons are on a carbon, which is directly attached to the carbonyl group. Then we have our 3 protons at the other end. These 3 protons are attached to carbon, which is single bonded to oxygen. So let's have a look through. We have proton, carbon, single bonded to oxygen, 3.1 to 3.9, but be careful, because if you have a look 2 down, you can see this proton attached to carbon, attached to oxygen, which is also attached to carbonyl as part of an ester group. Take care not to mistake those 2. So you've got your 3.1 to 3.9, 3.7 to 4.1. And yes, I appreciate there will be some overlap on those signals, but you will be asked to give the chemical shift in parts per million. So you need to be careful. Is it carbon single bonded to oxygen, say in an ether, or it could be an alcohol as well actually, or is it hydrogen bond to carbon bond to oxygen, single bond to oxygen as part of an ester? So just be very much aware of that. So they would have the chemical shift 3.7 to 4.1. So that's a common mistake and an easy mistake to make. You just need to keep your wits about you to avoid making that mistake. So that's chemical shift then. Let's move on. So one of the things that, one of the questions that came up before, so what if you have protons in different environments but the chemical shifts overlap? How can you identify one from another? Well, spin-spin coupling may well allow you to make that determination. This is probably the part of proton NMR that people find most difficult. It takes a little bit of getting used to, but I don't think it's that bad. Once you know what you're doing and once you know what you're looking for, it's not too bad, really. The reason it comes about, and again, this is probably going into a little bit more detail than you need for A-level chemistry, but it might help visualize what's going on. Because these protons have this property called spin, they essentially behave as mini magnets themselves. That means that they'll interact with an applied magnetic field, but they'll also interact with each other if they are up to 3 bonds apart. The individual magnetic fields of the different protons can interact. And when this happens, the signal undergoes a process called splitting, and it takes a different essentially a different composition. And the phenomenon is known as spin-spin coupling. Now, in order to determine the splitting pattern for the protons in a particular environment, you look at the carbon atom next door to the carbon atom on which the protons appear themselves. And sometimes it's a bit that people find hard to visualize. We'll have a look at a couple of examples in a minute. But you look at the protons, look at the carbon atom they're attached to, and then you go to the carbon atom next door and count the number of protons there. And it could be on the left and on the right. It's in the middle of a chain. We'll look at an example of that. You count up all those protons and you add 1. That's the n+1 rule. You add 1 to that number, and that gives you information on the type of pattern that you are going to get. There are some exceptions to spin-spin coupling. Okay, so you need to be aware of these. It doesn't occur between protons that are equivalent to each other. Remember, equivalent protons only produce one signal. And if they are next to each other in a chain, and they're on a carbon atom, they're not counted as part of the n+1 rule. They are not counted. Protons that are bonded to oxygen atoms don't undergo spin-spin coupling, and neither do protons that are bonded to nitrogen atoms. I put usually in brackets because there are some resources that indicate that this does happen. I'm not convinced that it does. I've had a look for spectra of molecules like methylamine and ethylamine, and the protons on the amino group always appear as a singlet. Sometimes they appear as a slightly broader singlet, but still usually a singlet. The reason for that, you don't actually need to know for A-level chemistry, but I'll mention it in a moment when we have a look at a couple of examples of spin-spin coupling. Okay, so these are the types of signals that we see. Remember, n+1 rule. So if we have a look at the first example, we have a proton here. It's bonded to a carbon atom. You look at the carbon atom next door. So it's not the carbon atom that the hydrogen is bonded to. That carbon atom's not important. It's the carbon next door, and you say how many protons are attached to that carbon. And in this case, there are none. So we say there are no coupled hydrogens, which means that that particular proton will generate what we call a singlet, a single sharp peak. The second example, we have our proton here. It's bonded to carbon. Again, we go 1 carbon next door, and we say how many protons are attached there. Well, this time we have 1. We apply the n+1 rule, so 1 + 1 is 2. This means that this proton will appear as what we call a doublet, 2 sharp parallel peaks. So third example, we have our proton here, it's attached to carbon, we go 1 carbon next door, this time we have 2 protons. We apply the n+1 rule, 2 + 1 is 3. That means that this proton here will generate what we call a triplet signal. I'll come to that question in a second. Last example, we have the proton in blue here. It's attached to carbon. Look at the carbon next door. 3 protons attached. So n+1 rule, 3 + 1 is 4. So we get what we know, what is called a quartet. So two parallel peaks in the middle, which are higher than the two on the outside. The J is just an indication of how far apart the different peaks are. And it's trying to make the point that the spacing is equal between them all. Well, the two tall peaks and two small peaks again. Oh, crikey. This will take quite a while to explain, but essentially it is to do with the number of spin possibilities that the different nuclei can have in terms of the coupling possibilities. I don't want to get too much into it now because it would take a little while to explain, but essentially that's what it is. There are different ways in which these two protons can interact, and then there are different ways in which three can interact. It's essentially related to Pascal's triangle, if I remember correctly, which those of you who do maths will know about. Okay, so those are the splitting patterns. So a couple of examples. There's a classic example. This is ethanol. So if we look at our methyl groups, we have 3 protons bonded to a carbon. Look at the carbon next door, 2 protons there. We apply the n+1 rule, 2 + 1 is 3. That will generate a triplet. Look at the protons on the middle carbon. Protons are bonded to carbon. The carbon next door has 3. 3 + 1 is 4. That will generate a quartet. Remember, the proton that's bonded to oxygen does not take any part in spin-spin coupling. It's not involved at all, which means that it's a singlet. And I said I'd give you a brief explanation of why this is the case. It's because the proton in the alcohol of the alcohol functional group, it can undergo proton exchange with the solvent, and that prevents it from appearing as a split signal. Again, for A-level chemistry, it's not something that you're expected to know. I think, if my memory serves me correctly, if you tried to do an analysis without a solvent and it was a pure sample of ethanol, I think you would see some spin-spin coupling. But because they're always dissolved in solvents and there's the chance for proton exchange, that doesn't happen. So it always appears as a singlet. So if you look at your signal, we have our triplet, our quartet, our singlet. Question coming in: if there was another carbon group when applying the n+1 rule, would you look to the left of the carbon only or to the right as well? We've got a couple more examples, and I think I might be able to clear that one up for you when we have a look at a couple more examples. Okay. So I think this one might help you here in terms of that question. Hopefully it will. If it doesn't, let me know. Ask me another question. So we have butane. We have 2 equivalent proton groups at the end, 2 methyl groups. The protons are attached to carbon, which is attached to CH2, so they appear as one signal. The 2 proton groups in the middle are also equivalent to each other. So this has 2 environments, which means it will show us 2 signals. So what about the spin-spin coupling patterns? Well, if we look at the methyl group on the left, and remember the one on the left and the one on the right will appear as a single signal. So we look at them one at a time, and we say that there are 2 protons on the carbon atom next door, i.e. this one here. Apply the n+1 rule, 2 + 1 makes 3. These protons will appear as a triplet. Okay, when we consider the protons on carbon 2, what you have to bear in mind is that these protons here are equivalent to these protons here, and equivalent protons do not take any part in spin-spin coupling. So these protons on the left are not equivalent to these, so they will take part in spin-spin coupling. We apply our n+1 rule, 3 + 1 is 4, so that will appear as a quartet, but these play no part. These 2 sets of protons appear as a single signal, so you can take one of them in isolation and that points you in the direction of what type of signal it's going to be. So they'll appear as a quartet. Just to make your point, there's a spectra for you right there. We have a triplet, just less than 1 for the CH3 group at the end, and we have a quartet for the CH2 group, with slightly higher chemical shift, which is what you'd expect because it's still classed as a CH2 R2 group. So you would expect it to be 1.2 to 1.4 in terms of its chemical shift, as per the table over here. So that's fine. Okay, one more example. What if we change our molecule slightly to 1-chlorobutane? Let's go through it. Well, take carbon number 1, reading from left to right. There are 2 protons on the carbon next door, so we apply our N+1 rule. The protons on carbon 1 will manifest as a triplet. Go over to carbon number 4. These protons are not equivalent to the protons on carbon number 1 because of the presence of the chlorine. So we have 2 protons on the carbon next door, so they will also appear as a triplet. I'll go through the rest of these signals. Questions come through, I'll go through the rest of these signals and then I'll answer that question. So then carbon number 2 and carbon number 3. We'll take carbon number 2 first. Now we have 4 protons either side. We have 2 protons on the left and 2 protons on the right. But the thing is, the protons on carbon number 3 are no longer equivalent to the protons on carbon number 2. And the reason is because the protons on carbon number 2 are bonded to a carbon, which is bonded to a CH2Cl group and a CH2 group, whereas the protons on carbon number 3 are bonded to a carbon, which is bonded to CH2 and CH3. The descriptions of the environments are different. That makes them different environments. That means that because they are not equivalent, the protons either side will take part in spin-spin coupling. So if we go back to carbon number 2, we have 2 hydrogens on the carbon to the left, 2 hydrogens to the carbon on the right. We apply our N+1 rule. 4 plus 1 is 5. Anything that is above 4, as far as AQA A Level Chemistry is concerned, you can class it as a multiplet. It would actually be a quintet in terms of its signal. Let's look at the protons on carbon number 3. We have 2 to the left, non-equivalent, and we have 3 to the right, also non-equivalent. That makes 5. Apply the N+1 rule. 5 plus 1 will be 6. So again, you'll have a multiplet. It would actually be a sextet in this case, but you're not required to know the names beyond quartet. Anything above quartet, you're allowed to call a multiplet. Now, a question came through just before. If it was propane, would the middle CH2 be a quartet or a multiplet? Good question. Well, it would actually be a multiplet because equivalent protons, a proton environment is not does not undergo spin-spin coupling with equivalent protons to itself, but the 2 CH3 groups either side of the middle carbon are not equivalent to the protons on the middle carbon. So it would actually be a multiplet. It would be a septet in this case. It would be 6 plus 1 makes 7. So just to make sure I've kind of got that idea across, if I just go back a moment, because I think it's a good point. So if you look at the case here, these protons here are equivalent to these, so they won't take any part in spin-spin coupling. But if this was propane and this was the CH3 group here, that CH3 group is not equivalent to that. That CH3 group is not equivalent to that. Therefore, both sets of protons can interact with spin-spin coupling with the protons on the middle carbon. I hope that covers it. I hope that makes sense. Okay, so moving past that, done that one. That's what the spectra looks like. So you have your triplet here, you have your triplet at the end. Clearly the triplet, which is much more shifted to the left, that will correspond to the protons that are on the same carbon as the chlorine. This triplet will be here, and then you've got your your quintet and sextet in the middle. Okay, that really covers it. That's pretty much everything that you need to know about NMR, covered fairly quickly, we're honest, but hopefully it's been a good revision for you. There was a question that came in just then. What's the tiny little peak? Ah, yes, I think that comes back to a question that you asked before. This tiny little peak in the middle. On this example, which I borrowed from the University of Sheffield, my old university, that was actually the reference peak. So I don't think they used TMS here. They must have used something else. I can't remember what it said in terms of what they used, but it's just the reference peak. They used a different reference in this case. Okay, so we're doing quite well for time, I think. So just to kind of wrap things up, I thought I would throw a couple of questions at you, just to see whether you're comfortable with this and whether you've got the hang of it. So this is from June 2014. So it's on the old spec, but it's still quite a good question. So 2 esters studied using NMR spectroscopy, and one of the 2 esters produced a spectrum, and it tells you, if I might just zoom in a little bit so it can make it a bit clearer. One of the 2 esters produced this spectrum. Can you deduce which one it was and predict the chemical shift value of the quartet in the other ester? It's worth 4 marks. See if you can work out which ester would have produced this signal, and you can type it into the group chat. You can just send it to me if you're not sure. We'll see who can get the correct ester first. I'll give you a moment or two to consider that. If you're watching the video on YouTube, you can just pause it for a second if you want. Do we have any takers? Which one do you think it is? You may need to use the chemical shift data to help you with this. So we've had a stab in the dark, ester 1, literally a 50-50 chance, as somebody has pointed out. So somebody else has gone for ester 2. I was hoping you might be able to be a little bit more confident. Well, one of you is definitely right. So let's bring up the mark scheme so you can see for yourself. Somebody else has gone for, I think, 1. Okay. It is ester 1. Absolutely right. Okay, so how can we determine that it is definitely ester 1? Let's get rid of the mark scheme for the moment. Let's work through it. The isolated methyl groups, they're going to produce a very specific signal. There are no protons on the carbon next door, so you know that they have to be a singlet. They can't be anything else, and you've got 1 singlet there. So then it comes down to chemical shift. So in ester 1, the singlet is next to a carbonyl, which you would expect to have a value of somewhere between 2.1 and 2.6. On the right, the singlet is next to your oxygen, which is part of your ester group. That has a value of 3.7 to 4.1. Well, you can see your singlet's at 2.1-ish, just over 2. So it's got to be ester 1, it can't be the other one. So the rest of the question, predict the chemical shift value of the quartet peak in the spectrum of the other ester, and then was it explain the position splitting the quartet peak at 4.1. Okay, well, it's a triplet, it's a quartet, sorry. So that must be next to CH3. So that will be that set of protons there, the CH2 group, and that's what you need to identify. And that also, I think, corresponds quite well to the chemical shift 3.7 to 4.1. The quartet in the other one, well, here's ester 2. Our quartet is going to be the CH2 group next to CH3, applying the N+1 rule, and that is next to carbonyl. So you would expect that to be 2.1 to 2.6. Let's just check the mark scheme. There we go. All the information for you right there. So if you're asked to explain position and splitting, you can refer to, if you have a look at the mark scheme there, you can refer to the type of structures that are used on the data sheet. As long as it's really clear which proton you are referring to, you can describe the structure in those terms. That's absolutely fine. Okay, we'll have a quick look at the other question. I don't know if you're going to like this one very much, but I think you need to see it. This is from the specimen paper, so it's a new spec question. You are given the infrared and the proton NMR of compound R, which has molecular formula C6H14O. Here's the question. The relative integration values are shown on figure 10. Deduce the structure of compound R by analysing figure 9 and figure 10. Explain each stage for 8 marks. So that's a big question, 8-mark question. I think what we'll do is maybe have a look at this one with reference to the mark scheme. If you're watching it on the video and you want to have a go at working it out, then you can just pause the film just now. So before we look at the mark scheme though, I know we haven't done infrared spectra today. You know that your molecule contains oxygen. I'm hoping that this broad absorption signal here on the left is telling you that it contains an alcohol, and that might help you a little bit to start off with. And the other thing is, we have a look at our proton NMR. We have 4 peaks. That tells you that we have 4 unique proton environments. Hopefully that's the kind of information you can pull out pretty much straight away. We have our relative integration values of 0.4, 1.6, 1.2, 2.4. The molecular formula is C6H14O. So we look at our relative intensities. Well, it looks like it could be 1 to 3 to 4 to 6, 1, 3, 4, and 6. That adds up to 14, and it's C6H14O. So we have a 1, 3, 4, and 6. The 1 will surely be the alcohol group. The 3 is a singlet, so we know that maybe we have 3 protons on a carbon that is bonded to a carbon with no hydrogens directly attached. And then we have 4 and 6, but they are equivalent. 4 and 6 equivalent suggests 2 equivalent ethyl groups. Here's the mark scheme. There it is. Okay, so first of all, the only thing you get from the infrared is that there's alcohol present. 4 different environments. The integration ratio indicates 4 to 1 to 3 to 6, which happens to add up to 14, which is quite useful. So the singlet with intensity, or hole number 1, that must be the alcohol. The singlet with relative intensity 3 must be a CH3 group with no adjacent hydrogen on the carbon next door. Quartet triplets, you'll see quartet triplet often in these things. That's indicative of an ethyl group, okay? Triplet is indicative of 2 CH2 groups joined together with carbons either side with no protons, or maybe oxygen either side, or nitrogen, or whatever. So there you go. There's the molecules I described it. You've got your methyl group, your isolated methyl group, so that will produce a singlet. Your hydroxy group of your alcohol will produce a singlet. And then you've got 4 and 6, but they are equivalent, so they must be 2 separate ethyl groups. So there is your alcohol. It will be 3-methyl pentan 3. Oh, that's quite a bit of information that you can get from those 2 spectra. So that's the level of question that you can expect on this in the exam. That concludes the webinar for today. I hope you found that useful. It will be released on YouTube in the next couple of days or so. I will stay on the line for a few minutes. I'm just going to get up and move away from the computer for a couple of moments. I will stay on the line though, so if you've got a question, another question that you want to check with me, stay on the line and type into the text box. If you don't have any more questions, like I say, I hope you found that useful, and I'll see you soon.
Very good.
Okay, I'm back again. I don't know if there's anybody still there who's got a question. Oh no, you've all gone. Okay, end the meeting now.